Hello there, I am Nathaniel Nelson, and today we will be talking a little bit about tensegrity, its applications, and its relation to physics. So you're probably wondering a little bit, what is tensegrity? I've never really heard of this word. Sounds a bit like integrity, but there's a T at the beginning. So its definition is a design principle that applies when a discontinuous set of compression elements is opposed and balanced by a continuous tensile force, thereby creating an internal pre-stress that then stabilizes the entire structure. To kind of sum that up in a bit easier, more digestible way, tensegrity is when a structure is held up by its tension forces and the elements that are in compression do not touch one another. Now that we've talked a little bit about what tensegrity means and given us a little bit more insight into what it is, let's talk a bit about its history so we can have some context for our further discussion. So a man named Buckminster Fuller, who also invented the geodesic dome, which is kind of like a climate-controlled dome that you can see in botanical gardens. There's one in St. Louis. He coined the term tensegrity in the 1920s, and then a popular sculpture artist named Kenneth Snelson started creating sculptures using tensegrity in 1949, and then they grew in popularity from there. A nice little fun fact about the intersection of tensegrity and its geometry are that the geometries are actually based off of and exhibit the forms of organic structures, so for example trees. So tensegrity kind of utilizes the mathematics behind nature to increase its structural stability and still be able to produce this effective form that is aesthetically pleasing and safe to use. Okay, now that we're feeling a bit more comfortable with tensegrity after talking about its history and kind of what it means, let's talk about some of its applications. So truthfully, tensegrity is kind of all around us. You can see it in things such as human anatomy, nanotechnology, and even big companies like NASA use it to improve and innovate with their equipment. For example, NASA is creating a robot to land on planets utilizing the geometries that are prevalent within tensegrity. This bot, when it lands onto the planet, will kind of smush into the ground and then pop back up into this little ball shape due to the compressive and tension forces that are so prevalent in the structure design. So tensegrity is actually a special type of structure and is called auxetic in the sense that it collapses in on itself rather than allowing for it to kind of switch out to the side like you would if you press down on a ball. So this kind of modality allows for NASA to utilize it for these different and somewhat uncommon tasks to help their missions be safer, better, and more efficient. Okay, so I know I just kind of said that the NASA robot would just planet and pop right back out, all good as new. But we're going to talk about the physics on that and why it works to make it seem a little bit less silly. So the main thing we're going to talk about is Newton's third law, which states for every action there's an equal and opposite reaction, right? So the two main components of tensegrity are tension and compression. So when you have these two components, they're going to mimic each other. So if I put one in compression, the other will go in tension, right? So it's kind of following, it's playing along, and this creates a net zero force, which allows for the structure to be very sturdy, very stable, and just very efficient. It allows for that modality, and it allows it to pop right back in place, because once it has this net zero, it always wants to go back to it, especially because of the elasticity of the tension members. So the NASA robot, once it crashes into the ground, it'll kind of pop right back out. Not because it didn't experience a collision, it definitely did, but because it wants to return and revert to that original shape. Another principle of physics that kind of relates to tensegrity is moment of inertia. So you can manipulate the moment of inertia to make a structure more stable. For example, it's specifically used with structures such as a floating table or a floating chair, if you're familiar with those. Essentially what they are two platforms that are held together by 5 strings and it looks like it's floating one above the other, but it's truly held by these two compressive and tensile elements. The moment of inertia comes into play in the sense that you can manipulate the center of mass to provide a greater structural stability from a relative standpoint. So, for example, if I had a tensegrity table that was flat, I could push down on it really hard and it would be very stable. But if I pushed it to the side, it would fall over instantly and be not very helpful. So the moment of inertia really helps in that one-dimensional frame, but once you take it to 3 dimensions, it makes it a lot more complicated in how you can manipulate that relationship. But overall, I think tensegrity is a very practical and promising design principle that can not only be utilized in architecture, as I mainly do, but in things such as physics, mathematics, chemistry, biochemistry, almost any field. I could see it in baking, honestly. Some nice tensegrity bread. But overall, I think tensegrity is a wonderful principle and very instrumental to how we may understand the world in the future.